This is the first recording in the deep dive series, and it is going to start the same place that I would start if I were doing anything else, and that's with the merge. Right. The first thing you have to do is discovery. You have to figure out who your neighbors are, how to route to them, where the rest of the network is, all that stuff. So the mechanism we use for this is a combination of HTTP using Rust and services. Okay, so conceptually, the process is fairly simple. What you do is you look at your machine, you look at the interfaces on your machine, for example, ETH0, WLAN 0, WLAN 1, and you for each interface that has a remote connection to it, you probe that connection and see whether or not it's a frognet. Now, how do you know it's a frognet? All frognets are set up to answer a bunch of basic questions. The most basic one of those is what are you? What is your name? Who are you? And you get that with a frognet echo. So you have an IP address that you're connected to, say through WLAN 0. You connect to another frognet upstream. You have an IP address that ends in 47, which is the IP address of your WLAN 1 or WLAN 0 node or interface. If you query that very address, it will go to the frognet host on the other side, and it will return to you the frognet identity of that host. So with that, you know who the host is and what its IP address is, because Frognet, the Frognet under Echo PHP call is it returns the IP address and the name and a couple of other pieces of information that aren't super relevant anymore, but they were there when I put it together, and I never took them out. We can look at it real quickly here. So, like I said, every single frognet answers this question. So you can see the frognets over here: Seattle 3 or Seattle 2, Seattle 6, Seattle 5. So we're going to look at BA box, and we're going to do a curl colon //. Now, every network, every one of these is a network, right? Everything that is here in Frognet Monitor, it is a network. So every network has a machine named Frognet host at its .1 address, and we know that that's by rule. So you can curl Frognet host dot BA box Frognet echo PHP, and it returns to you, this is the name of the domain, BA box. This is the name, or this is the IP address of the .1 machine there. And then these two are its upstreams on WLAN 0 and WLAN 1. Like I said, these aren't used very much anymore, but you can see here that this has a non-10 dot upstream, which means that this is a machine that is connected directly to the internet, specifically through that interface. Actually, it's not necessarily to the internet, but it has an upstream that it goes going through that interface. So we assume it's to the internet because it got here. So this is the first thing it answers. And with this, I can say, okay, I can establish a route to a machine name, to a network named BA box, and it is going to go through IP address 10.155.155.1, which is reachable through interface WLAN 0, right? So now I know how to get to BA box. That's not good enough. The next thing I need to know is who it knows, because I'm building a map of the entire network. So I find out who BA Box knows by asking it, right? I say get host. And it returns to me a JSON string that, it looks a little weird and it's compacted, but for each entry in here, there is an IP address, a name, and then its Frognet echo. So you can see that this entry here is for New York 1. What this means is that I can establish a route to New York 1 through BA Box, right, and to that IP address, because I assume that BA Box, right, since it's got it in its host table, BA Box can reach it. Now that route may be circular. It may come back through my interface. I can figure that out. But what I'm doing is I'm finding out who is the host and then who the host knows. And then for every one of these, we do the same thing over again. We go and ask it who it is, which I know is redundant because we've already got it right here, but we do it anyway. We ask them who it is, and then we ask who their children are. And so by doing that, we make a map of the node, the node's children, and the node's grandchildren. And if you do that about twice, maybe 3 times across even the most complex network, it all resolves. And what we're trying to do is get a host table that has all of these in it, right? And we're trying to get a routing table that shows where the routes are going and how they're going to get there. So we can look in here and we can say that to get to the 10.160.160.1 network, we are going to go via ETH0 10.250.250.221. So since it's on ETH0, we can do a cat of /var lib miscellaneous dnsmask.leases, and we can see right here that this is in fact the Frognet host. And I can ping down there, so I can curl that and do a Frognet echo, and we see that that is Seattle 6. So I can go down there, get Seattle 6, and then I can set a route that says I can get to this network via this address, whatever it was here, this address, right? So that's what this is saying. The 160.1 network is via that address. Now, all the other addresses are going to come through here too. So the 120 is a child of 160. And so it's also via the 221. All we do is we go to the next hop. We don't try to make a full route out. We just go to the next hop and we say, this is you, this is you, this is you. Now you'll notice over here on Seattle 5, if I do an IPR, we've got more routes that come up. Some of these are through ETH0, and some of them are through WG0, WG WireGuard tunnels, right? And then I assume that's right. These are all on Seattle 5. We have WLAN 0 is going to the internet. Okay, so WLAN 0 is carrying the traffic for the WireGuard tunnels up to the broker, and the broker is taking them through to the other side where the New York machines are. Okay, so with these two pieces of information, we can set up and establish the routes for the entire network. Now, how do we tell that it's a circular route? We tell it's a circular route by sending a request to it that it reply. We send like a Frognet echo to it. except that along the way, every hop along the way increments a counter. And so if we get it back and that counter is not 1 or 0, then we know it's a circular route. And we know it's a circular route, we don't even do it, right? We don't do that. So that's how we do basic discovery. And we set up the host table, and we set up the routes that way. But we do more along the same way. We also configure and set up DNSMask and the resolver. Okay, because as we find these routes, as we find these remote machines, we need to be able to send DNS requests to them and have them resolve, so that we can do, for example, an NS lookup of brokerhost.seattle2, and it finds it by name, right? That happens through etc. DNSMask .d/frognet forwarders auto. So for every machine that it discovered in etc. host, there's an entry here that says what it is and what its IP address is. This is what lets it be a name server. Okay, this listen address that says this is our address. We are listening for things on 250, 251 right now. Over here on Seattle 6, I think that's who we are. Let's see, Seattle 5. Okay, let's look at it here on Seattle 6. This is Seattle 6. So we're going to cat / etc. DNSMask.d forwarders, frognet forwarders, and we can see it's got the same entries, right? So this looks the same, except that the listen address here is different, right? So it's the same thing. By doing this, we can set it up so that we can do a NS lookup from anywhere on the network, and we'll find it. Okay. The resolve.conf that we used to use for this kind of stuff, I'm still setting it up, and actually I probably need to change this because it's the default route that I'm worried about. So I need to change this back. Nominally anymore, you can't have more than 3 name servers in your resolve.conf. It ignores anything more than that. So in this case, it's going to get 127.10.160 and then 120. We really wanted to get the 250, but one of these has that, so it's still going through. So if we do a trace route to 10.2 or trace route to google.com, we can see it goes to Seattle 5, and then from Seattle 5 it goes to the internet, right? And then it goes out from there, right? So that's what I expect when I see this, and that way we support DNS across the entire network. So when we get done with the merge, we have Network Manager running and it's ready to go. We have DNSMask fully configured so that it can do IP forwarding and name service resolution and all that kind of stuff. Every frognet on the system, its .1 address is a name server for the network that it is hosting, right? And the internet tunnels allow us to make the routes cross through the broker to the other side. That's discovery. Now, if you think about this, what you're going to notice is that we have a lot of JSON that's flying around back and forth. Every time we see a new one of these nodes, we're going to go ask it who it is, and we're going to ask who its children are. And we're going to do that over and over and over again for all the nodes in the network. And we're going to do it repeatedly, right? Every single node has to ask every other node. That's a lot of traffic, right? And in fact, if you did it in the traditional Rust way, you would be overloading the network. You would be absolutely crushing the network. So that's where semantic compression comes in. That's the next step that we want to take a look at. But semantic compression is a way that we can reduce the amount of data that we're sending in between these nodes during the discovery process, and really for everything that we send across the LAN, from kilobytes and megabytes to bytes, right? Potentially as low as like 21 or 24 bytes. And that saves a ton of stuff on the wire. And at the same time, we increase performance. So that'll be in the next video, where we are going to be talking about and introducing semantic compression. And we will look forward to seeing you there. Thank you.